Alright, so we're going to take a look at Coulomb's law, the relationship between electric charges and electrical forces. In 1700s, a scientist named Coulomb came along with a relationship between charges. So say I've got a positive electric charge here, we'll call that charge 1, Q1. And say we have another electrical charge, make that a negative charge over here, we'll call that Q2. And so we have a positive and negative. We know that those forces between them would be an attractive force. So we have a force, electrical force here, and electrical force there. Those would be the same amount of force. And he looked at the idea also of how far apart they were. So how did the amount of charge and the distance between them actually affect the actual, how does it affect the force between those two charges there? And so he came up with the relationships as follows, that the electrical force is proportional to the product of the two charges, and that electrical force is inversely proportional to, or proportional to the inverse of the distance between them squared. So this is very much like the gravitational law that Newton came up with, except instead of charges, you're talking about masses with gravitation. And so you get a very similar relationship, as increasing the charge will increase your force, but increasing the distance is going to decrease your force. So from that, you have an equality when you say the electrical force is equal to the product of the charges divided by the distance between those charges squared. So it turned out then, as they were doing the calculations, you get an answer, a number, a value for your force. And they did the actual measurements with the laboratory equipment, and these two numbers didn't match each other. So the electrical force just did not equal this. But if you take the two things here and you kind of divide what you got here, this answer, into this answer over here, you kept getting the same result. There's still the same ratio between them. And so this is what's known as the electrical constant. So the value K, put right in here, is the electrical constant. And it's the same in every situation. I'm talking about electrical forces acting between different charged particles. So electrical constant worked out to be about 9 times 10 to the 9th power, so about 9 billion in terms of its number, and the units are going to be newtons times meters squared over Coulomb squared. So we've got the unit of force in here, we have the meters squared, and we have Coulomb squared. And recall the Coulomb is the unit for electric charge, also named after Coulomb. We'll come back to why those units are what they are as we go through the example here. So let's put some specific numbers here with these charges. Let's go ahead and say that Q1 is a positive 5 coulombs, and let's say Q2 is a negative 7 coulombs. Now, in reality, these are some really, really large charges here. Most everyday stuff is, in orders of, a millionth of coulombs and things like that. Remember that we had 6.25 times 10 to the 18th electrons, right? That would equal 1 coulomb, a negative coulomb. So these are really big charges, but the numbers are a little bit easier to work with than maybe some of the more realistic ones you might see later. Let's say the distance then between them also is something a little bit more everyday kind of size for right now, about 2 meters between those. So what we want to do is find the electrical force between these two particles, right? We already know it's an attractive force, we just want to know the actual size of that. So we're going to take the K value and multiply it times the product of the charges and divide it by the distance squared. So we're just going to leave the K for now as it is. We'll go ahead and substitute in the charges, so the plus 5 coulombs times the negative 7 coulombs, and all that divided by the distance, 2 meters. Don't forget to square it. Take all that. So the reason I'm just leaving the k like it is right now, so we don't have to have all of this going on within everything. It can be a very confusing looking equation as you work through everything. All right. Let's do this. Let's say, kind of keep this in parentheses by itself as well. Right. Kind of separate these guys out, so we're not thinking there's a subtraction happening in there. So 5 times 7, or times negative 7. And so we're going to take our electrical force, we're going to keep our k here, and so we get a negative 35. And coulombs times coulombs will give me a coulombs squared. And then on the bottom here we have 2 meters squared, so we get 4 meters squared. That's all that stuff in there. So let's kind of finish this out now. All right. Might need a calculator for this one, but the negative 8.75 coulombs squared over meter squared. So this would be what was calculated, when originally developing this law and this relationship, and the electrical force was expected then to be the same value, and well, it's not. They don't match. So this electrical constant has to be incorporated here. So we need to come over to the side here now. Let's take the electrical force, and let's go ahead and put in the value for k in here. 9 times 10 to the 9th newtons times meters squared per coulomb squared. Alright, and so we'll multiply that times our negative 8.75 coulomb squared over meter squared that we had previously determined over here. Alright, so multiply all this together. Remember, that's just 9 billion. You can put this in your calculator just like this, or use 9 billion if it makes you feel better, but you get the same result in the end. You get 7.88 times 10 to the 10th. And so now we need to deal with those units. Alright, I mentioned that the units for K was newtons times meters squared per coulomb squared. Well, here's why. These coulombs squared here and coulomb squared here will cancel out. The meter squared and the meter squared cancel out, and that leaves you with newtons, which is the unit of force. That's what we should get here, a force of 7.88 times 10 to the 10th newtons. So now I'm looking at this and I just realized I missed this minus right here. Right, did you guys notice that? So I forgot that little minus there, so I'm going to put that right in here because that should still be there. And that's important because what that's telling us in this case, since we look at the picture, look at the context, well, that's an attraction that's taking place there. So that's giving you some idea of the direction of the force. And with charges, we're talking about, was it attracting or is it repelling? So we have an attractive force, an attraction taking place when we get that negative force as a result. If we had a couple of positive charges, right, instead of a positive and negative, right, if we had a positive 5 coulombs and a positive 7 coulombs, we'd end up with a positive force, and we know that's going to be a repel. Right? We're going to have what's called a repulsion taking place there. And similarly, if we had a negative and a negative, right, negative 5 coulombs and a negative 7 coulombs, there's still going to be a repulsion. And negative times a negative is also going to give us a positive. So in both cases, we get a positive force result. And those are both talking about repelling, those situations there. So that sign does mean something with our force because it is indicating a direction in terms of attractions and repulsions. So there you have Coulomb's law.